up to this point, we've been living in the mythical world where there is no friction. Now we're going to introduce friction. We're sophisticated enough, we're ready to handle this in our force diagrams. So we're going to talk now about a friction force. And there are two types that we're going to focus on. And then there's some types we're going to mention, but we're not going to do much in the way of calculations for. And these are, first of all, surface friction. This is friction between two surfaces when they rub together, like when you rub your hands together, or when they're just in contact. So they're static when things are just sitting still. So I have a block and it's not moving. And this one is a little tricky because we can think about it. When you have a block that you cannot move or you don't move, you push on it just a little bit. So here's your force of push. Then what happens is friction opposes your motion. That's static friction. And if you increase this push and this block still doesn't move, then that means your static friction has increased. Everything's balanced, it's at rest, and it's not going anywhere. There's no acceleration. And friction opposes the motion. So it opposes motion, and static friction at least can adjust, right? If you push even further, you may get to the point where it gets bigger. Like if it matches it, okay, it doesn't move. But if you push even further and it gets to the maximum value, then you get a situation where I'm going to make my push bigger, and this is Fx max. Then, of course, we're going to have an acceleration to the right, and we're going to start moving, and it's not going to be static friction anymore. So this maximum value can be given by what is the contact force. Because it's dependent on the contact, we say that friction static is the maximum value is equal to some coefficient, this mu sub s for static friction, times the normal force. Okay, so friction force, this is measured in newtons, this is measured in newtons, so this has no units. It's just a number, like 0.5 or 1 or something like this. And this depends on the two contact surfaces. Like, is this a wooden block sitting on ice, for example? That would be low friction. A wooden block sitting on a rubber mat, that would be a high coefficient of friction. So in general, this is the equation for maximum. In general, our static friction is less than or equal to this maximum value. And the maximum value is the one we reach right before it lets go. Okay? And it depends on the normal force. So if you increase the mass, that's going to increase the normal force for a block sitting on a horizontal surface. And so that will increase the friction. That shouldn't be a surprise. You take the same block on the same surface. If it's a heavier block, it's harder to push. Okay, kinetic friction. So we'll look at kinetic. That's of motion. And so that's a little easier. This is when something is moving. Let's say it's moving this direction. That's the direction of V. Then kinetic friction just works always to oppose the motion. It doesn't matter what direction you're going, it works to oppose the motion. And what's happening is that you've got atoms rubbing against other atoms, and you get them sort of a bumpiness in between, and so this rubbing creates heat, and that's where your energy goes as we slow things down. So kinetic friction is along the surfaces, and it's opposing the motion, and so we're going to call this F sub k for kinetic friction. And this, there's no less than equal kind of thing. It's just equal to the coefficient of kinetic friction times the normal force. And this coefficient for the same two surfaces, the coefficient of kinetic friction is less than the coefficient of static friction for the same two surfaces. And I have to say this mu is sort of an average value because depending on the material, you can have different places where you have imperfections, so you can slow down, you can have a bigger or smaller force which results in a bigger or smaller acceleration when something's sliding across it. So you can have imperfections, obviously, even if you think you have a really smooth wooden surface. Wood is not a uniform surface, but it's an approximate value. And it works well for what we want to do. So if we look at sort of a very simple case where we have a block that was pushed at some point in the past, and it's just slowing down. So it's going in that direction, that's the direction of V, and maybe it comes to a stop right here. Then if we draw a force diagram, we can say, hey, we've got mg, and in this case, because it's not accelerating up or down, we have force normal. That's our force diagram. The only other force we have in this case is just going to be this friction force. And this friction force is what provides the acceleration. And notice, even though it's going to the right, there is no force to the right because that's the direction it was going. It wants to keep going that direction unless there's a force acting on it. And there is a force acting on it that slows it down. And so if we look at this in the x direction, then we have k, which is in the negative direction if you like, is equal to ma, also in the negative direction because a would be in that direction. And in the y component of motion, we just have force normal up minus mg is equal to 0, no acceleration in the y direction. And so we get then that force normal is equal to mg. We can plug that in here to realize, for example, this is, I'll get rid of the minus signs, I get mu times force normal, which is mg, is equal to ma. The m's cancel, and our mu is just equal to the acceleration over 9.8, or about acceleration over 10. So this gives us a really easy way to actually measure this coefficient of kinetic friction, because from that I get mu sub k is equal to a divided by g. Okay, that comes from this. I'll rewrite it a little higher because I'm about out of space. So from this I can get mu sub k in this particular situation is a over g. So if I measure this a, I can find my coefficient of kinetic friction. An easy way to find the static friction, the coefficient of static friction, is to adjust the normal force. So notice that as your normal force, as you tilt this up and up and up, because your normal force is perpendicular to the surface, it gets smaller and smaller because your weight always points down, like this is the weight, and then this is the y component. Oh, I didn't make that to scale at all. This is my mgy, which my normal force has to be equal to. So it's got to go like this, force normal. But as I tilt this more and more, this right here gets smaller, and so my normal force gets smaller. Because when this is tilted all the way up, notice there is no normal force. So my normal force gets smaller, and so what happens is this mu s is whatever it is, so my maximum friction force is getting smaller and smaller. The amount of friction I have available to keep this in place gets smaller and smaller. If, for example, right now this is not moving, so you can think of putting something on an incline and raising it up and it doesn't slide. It did slide there. But you can think of doing that on a tilted surface. Then we know that we have the component, the mgx component, that's getting bigger. And then we have, in this case, this is wanting to oppose the motion. So what happens is this weight wants to pull it down. It says, no, no, I want to stay. So this opposes it. So we have fs, which is adjusting. And as we go, we get to the point where we just lift this angle up just enough so that these are equal, and then it starts to slip, right? So what happens is this is just a little bit bigger than this, and so it starts to slip, so we can find right at maximum, at the maximum value of fs, we really have a situation where basically fs minus the x component is basically equal to 0, slightly more, slightly less than, right, 0. We have a little bit of acceleration, but we'll call it essentially equal to 0. This is in the x direction. Because as we tilt up just a tiny bit more, these are no longer going to be balanced because this can't get any bigger. So we're right before it slips is where this is our maximum value. And that'll give us, if we can measure this angle, that will give us our static friction. And even better, that's the x information, we can also write our y component forces. And so our y component forces tell us that we have force normal up minus mg, the y component, must be equal to 0, right? Because it's not accelerating in this axis. Again, just to remind you, when I've got this tilted situation, I don't think I said this, but this is your x and your y axis, as we've done a bunch of times before. And so using just a little bit of trig, this gets us Fs, the x component, this is theta, this is also theta, so the mgy is the adjacent one, so that's the cosine one. Mgx is the opposite, so that's the sine one. So this gives us f of f sub s, the maximum value, is equal to mg sine of theta, just substituting in for the x component as mg sine and moving it over. Same thing here, we have Fn is equal to mg cosine theta. So we can say our f sub s max, because that's where we are, is equal to mu sub s f n, or mu sub s is equal to f sub s over f sub n. And if I plug in these two values, that just gives me sine of theta over cosine theta, because the mg's cancel out, which is equal to tangent of theta. So this gives us a fairly easy way to find our coefficient of static friction between two materials. We can just tilt things up, and from that we can find right before it releases what this angle is. Now once it releases, because the coefficient of static friction is bigger than the coefficient of kinetic friction, it will actually accelerate down, and we'll be looking at an equation where we would be putting mu sub k times our normal force, which would be at an angle. So mu sub k times this would be the force, the x component would be our force to calculate, say, the acceleration. So we would have a new equation here that would say F sub k, kinetic friction, minus mgx is equal to ma once it started moving down.